Swayam Prabha. Digital India. Educated India.
So my name is Manoj Kumar Ramdeke, and the topic on which I am going to present is multi-objective and multi-salesman extension of traveling salesman problem for real application. Okay, so the outline of the talk will comprise of we will start with route optimization, then we will discuss the traveling salesman problem and its applications. Then the algorithm which we have developed recently, that is two-stage evolutionary algorithm for solving multi-objective traveling salesman problem, and its extension for dynamic problems that we will discuss, and finally some applications. Okay, so if you look at the e-commerce companies, so one of the important problem in the e-commerce companies is the last mile delivery. So a typical schematic of the last mile delivery is shown here. So you can see here that there are almost 7 pickup locations and there are 6 delivery locations. The objective here is these agents has to pick up the parcels from these locations and also deliver the parcels to these locations in minimum distance and minimum time. That is what the objective is typically. So this problem looks very simple here, but it's not very simple. If you look at the real applications where large number of parcels are there, this problem is combinatorial and you will have exponential time complexity. In fact, a similar structure we can see even in process applications. So for instance, if we take the example of polymer grade scheduling, so we can consider that all these 13 are polymer grades. And let's say the problem is to schedule these grades in different extruders. So here extruder 1 and extruder 2. How we can optimally schedule these polymer grades in different extruder in order to minimize the mix stand. That can be the problem. Another interesting example here is it could be a drone scheduling where drone has to deliver the material at different locations, also for military applications, vehicle routing, and many other problems like maritime surveillance, where the ships are located in the ocean and the helicopter is used for monitoring these ships. So there also the distance minimization is the objective. Other objective could be to minimize the time. So all these applications you can see that commonly have a network structure like this. And from this network structure, one has to find out the optimal route. So that is what the bottom line of all these problems are. And if you look at the importance of all these problems, these are extremely important problems. Why I'm saying these are extremely important? So if you look at all these e-commerce companies, so if you see the 10 biggest economies, the reason for their development is primarily because of the boom in these e-commerce companies. In fact, if you look at the last 5 years, there is almost 140% surge in the business of these e-commerce companies. But each of these e-commerce problems, if you look at, the 60% of the cost is primarily because of this such last mile delivery. So these problems are extremely important. Other than the economies, these problems are also important for the security purpose. For instance, in this particular graph, you can see that there are several locations are there, and these are the locations where there are attempted attacks, fired upon, hijacked, suspicious vessels occurred on the vessels in the sea. So if you look at the transport through sea route, almost 95% of the international trade occurs by volume and 70% through a marine access. And in the last 8 months, if you look at the number of incidents for the piracy and the armed robbery, you can see almost 90 incidents occur for the robbery and the other problems. So in order to avoid the terrorism, piracy, illegal human traffic, and narcotics, solving such marine access monitoring of the ships is extremely important. Again, so see, mostly people do it by using the satellites, but satellite is not going to give you the close information. So for For close information, typically people utilize drones to monitor the ships. The other option is to use the helicopter to monitor the ship. Okay. So in such problem, the objective is to minimize the time, minimize the distance. So same route optimization problems comes into the picture. But the difference in this case is, in this particular case, even these locations are moving because ships are moving in the sea. They are not static as these locations here. So that gives to a dynamic traveling salesman problem. Okay. So if you look at the traveling salesman problem, the simple definition is the salesman has to visit the number of cities such that he visits to each city only once, and while doing that, the distance has to be minimized. That is what the traveling salesman problem is. If you look at this particular figure here, we have used 653 cities in India. And if you have noticed that the initial figure, we had all zigzag connection for the random connection of the route. But as we optimize the route, you can see that very ordered route we can get here. In fact, in this case, you can see there is no cross connection at all. So this is the optimized route which we have obtained using our own algorithm. So you can see that the starting is zigzag, but then once you optimize it, all these cross connection goes away and you get a very good route in this case. So this is a typical traveling salesman problem. So this problem we have solved using our algorithm, hybrid local search evolutionary algorithm. And their extended version is two-stage evolutionary algorithm. We have obtained this optimum result only in 30 generations. So in this case, the optimum tour length, you can see that for these 653 cities, it is around 36,000 kilometers. If you wanted to visit all the cities in India. Oh. Okay, so as I said that this problem is extremely important. And typically, these problems are solved using local heuristics. In fact, if you look at the local heuristics like Lean-Kernighan algorithm, they are able to solve even the problem with 10 lakh cities. Okay. But the problem with this local heuristic is, if you look at the real life applications like e-commerce business, e-taxi business, maritime surveillance, or even process scheduling, they involve multiple objectives. It's not only the distance you are interested in minimizing, but also you are interested in minimizing the time. Again, the other objectives could be, sometimes you are interested in maximizing the customer satisfaction. You could be interested in minimizing the emissions. So all these multiple objectives are naturally present in this problem. So when it comes to such local heuristics, these are having some difficulties in handling multiple objectives. Another difficulty is, so see, a typical traveling salesman problem has only one salesman. If you look at the real life application, in real life application, you have multiple delivery agents. You can have multiple helicopters to monitor these ships. You can have multiple agents to visiting the delivery locations, isn't it? So multiple delivery agents are there. And the third important challenge is a dynamic variation. So as I said, in a maritime surveillance problem, even ships are moving. They are not static. So continuously they are moving. So you have to keep the track of time. Because every time you make the decision, some time is elapsed, and during that time, the location of the ship is changing. So all that you have to account in the optimization. So clearly solving such problem, real life problem with these challenges is not easy, even though the local heuristic based algorithms are good for handling the combinatorial constraint and solving the single objective problem. But when it comes to these challenges, these are having some difficulty. Now, as I said that these local heuristics are good for solving the single objective problems. But when it comes to multi-objective, the algorithms which comes in our mind is evolutionary algorithms like genetic algorithm, particle swarm, or differential evolution. Even though they are good in solving the multi-objective problems, their issue is primarily to handling the combinatorial constraint. For instance, in a traveling salesman problem, the constraint is the salesman has to visit each city only once. If you perform the crossover in genetic algorithm, what happens typically in genetic algorithm? The genetic content is swapped at the crossover site. So if you are swapping the genetic content and obtaining the offspring solution, what you will see is this particular combinatorial constraint will be violated. It's not going to satisfy readily. So all these operations which are present in these meta-heuristic algorithms has to change for solving the combinatorial problem. That is the challenge. Okay. So in this case, what we have done is we have combined the advantage of this local heuristics and also the advantage of meta-heuristic algorithms like genetic algorithm to develop the new algorithm, which is local search based algorithm and two-stage evolutionary algorithm. So in this case, we have combined the advantage of both these algorithms. So two-stage evolutionary algorithm we have developed for solving the multi-objective traveling salesman problem. So let's look at the formulation of this particular problem. So typically, the location coordinates we know in such problems. So in this case, xki and yki, these are the coordinates in these are the coordinates of the cities in the kth plane. Why I'm using this word kth plane? If you are solving a single objective problem, in that case, this k is 1. But when we are solving the multi-objective problem, then this k is varying from 1 all the way to m. So we are solving m objective problem. There are m planes, and in each plane we are minimizing the tour distance simultaneously. We are minimizing the tour distance in each plane simultaneously while keeping the index I common in all planes. So here the objective is to find out the sequence of the cities such that the tour distance in all m planes has to be minimized simultaneously. So here you can see that this dkij is the distance between two cities I and j in kth plane, and this distance has to be added for all the cities to get the tour length. So this is the tour length for the kth plane. In a similar manner, we can obtain the tour length for all the kth plane, and this we can minimize simultaneously. Okay. So as I said that we have developed the algorithm which is hybrid local search evolutionary algorithm, and then we have extended it to a two-stage evolutionary algorithm. So clearly this genetic algorithm, non-dominated sorting genetic algorithm, we have extended to hybrid local search evolutionary algorithm. The difference here is the typical operations which are there in genetic algorithm, these operations we have replaced using new operations. For instance, you can see that in a genetic algorithm, typically we start with the generation of initial population. In a conventional genetic algorithm, the initial population is generated randomly. But in this case, we are generating the population using the nearest neighbor heuristic. Again, I will explain this nearest neighbor heuristic in a little bit more detail in the subsequent slides. Once the population of these NP solutions are generated, these are assigned with the rank and the crowding distance. And then we perform the mutation, the guided crossover operation. So in guided crossover operation, what we do, we select one solution from the entire population. That is the parent 1. And parent 2 is selected from the best solutions. So best solutions are those solutions which are having rank 1. Or if you are solving a single objective problem, the first 10% solutions can be considered as the best solution. So we select randomly the best solution and one solution randomly from the entire population. So parent 1 is selected here and parent 2 is selected from the best solution. And we perform the crossover between these two solutions. So again, unlike the conventional crossover where genetic content is swapped, here we are using a guided crossover where the nearest neighbor heuristic is used for performing the crossover instead of swapping the genetic content. That is the difference. Third operation which we have modified is a mutation operation. So typically in a mutation operation, what we do, we change the gene, tweak the gene here and there. That's what we do in a usual genetic algorithm. But here we are using a 2-opt heuristic in a guided mutation operation. And then the rest of the procedure is nearly the same as the conventional GA. We obtain the offspring solutions. These offspring solutions are mixed with the parent solution, and best NP elite parents are obtained in the elitism operation, and this cycle continues for many number of generations till we get the optimum solution. Now the problem with this algorithm is, even though the idea was good, idea was combining the advantage of both meta-heuristic algorithm and local search. But what we have seen is when we apply this particular algorithm for multi-objective traveling salesman problem, it only generates the part of the Pareto. It does not generate the complete Pareto. And there is a reason for that, why it is not generated. So what we have done is we have extended this algorithm to another algorithm, which is two-stage evolutionary algorithm. As the name itself suggests, the two stages of this hybrid local search evolutionary algorithm is used in this. So what we are doing in this two-stage evolutionary algorithm, in the stage one, if let's say there is a M objective TSP problem is there. So all these individual M objectives we solve as a single objective, and we obtain the corner solutions of the Pareto. We obtain the corner solutions of the Pareto front. And these corner solutions of the Pareto front then used in the second stage as a initial population. So we are feeding these corner solutions as an initial solution in the second stage, and then we are solving. When we are doing that, we are able to get the complete Pareto front, unlike this in the same number of generations. Same number of function calculation, we are able to generate the entire Pareto front in this case, unlike this case where only the part of the Pareto front was generated. So I will explain why this is able to give the complete Pareto front and why it gave only the part of the Pareto front in the subsequent slide. Okay. So as I said that we will look at the nearest neighbor in little bit in more detail. So this is the slide on nearest neighbor. So initial population we are generating using the nearest neighbor. You can consider a simple illustration here. These are the 6 cities are there. If I randomly connect these cities, I am going to get a random tour like this, isn't it? So clearly there are several cross connections are there. So this is not optimum, isn't it? But when we apply the nearest neighbor, for instance, let's say we are starting with this city 1. The nearest neighbor for city 1 is 4, so we will connect to 4. For 4, the nearest neighbor is 6, so we will connect to 6. So 6 is the nearest available city. And in this manner, we will generate the entire tour like this. So you can see that there is no cross connection. So this is much better solution compared to a random tour. So in a initialization, if we generate the solutions randomly, and if you generate the solutions using nearest neighbor heuristic, you will see that the initial solutions generated using nearest neighbor are much better in quality compared to this. So again, so see, even though this nearest neighbor will give you a reasonably good quality, but it will not give you the optimum, because in this case only 6 cities I have shown. But let's say if the cities are 100 or 1000, in that case you will see some cross connections will be there. It's not going to completely eliminate the cross connection. So again, these sequences of the cities are then represented as a chromosome. So in this case, the chromosome is nothing but 1, 6, 5, 2, 4, 3. These cities indexes are arranged in a string one after another, and that represents the chromosome. So this is what we are doing in a single objective. But let's say multi-objective is there. So in multi-objective, you need to find out the nearest neighbor with respect to all M planes. In this case, only single plane we are looking at, which is here in the figure. But in multi-objective, there are M parallel planes are there. So in such cases, what we are doing is we are assigning the random weights to all M planes, and we are summing up their distance, and that weighted distance is used for applying the nearest neighbor. Then the next operation, as I said, is a guided crossover. So typically in a crossover operation, what happens is genetic content swap. So this is the parent 1, which we have selected randomly from the entire population. This is the parent 2, which is selected from the best solution. But in this particular case, what we are doing is, instead of doing a swapping of the genetic content at this crossover site, what we are doing is we first identify the crossover site. And once we have identified the crossover site, all these city indexes after this crossover site we are deleting. So this part is deleted. Now in the second parent, what we are doing is, so all these cities which are retained in the original parent 1, these are identified here. So these are 4, 3, and 5, and these are again deleted from the base solution. So if you are deleting these 4, 3, and 5, which are already there in this particular sequence, in that case, whatever the remaining city sequences are, which are nothing but the remaining cities which has to be here, isn't it? So if we delete it, what we get is we get the chunks. We are getting the chunks 1, 6, and 2. And then the chunks are connected from this point, this crossover site onward in a nearest neighbor manner. So this particular procedure is called as nearest neighbor on chunks, because we are using the chunks here to connect. For instance, here, let's say the nearest neighbor for 3 is, let's say, 6. In that case, the sequence I'm going to attach here will be 6, 1 in a reverse order. But let's say the nearest neighbor to 3 is 1, then I'm going to connect 1, 6 in a forward order. So in this particular case, the nearest neighbor is 2, so 2 is connected first, and then 1, 6 is connected. So this is the perturbed new solution we have opted. So unlike a usual genetic algorithm where the crossover of two parents gives you 2 offspring, here the crossover of 2 parents is giving only 1 offspring, not 2 offspring. Okay. Again, so the nearest neighbor procedure which we have used for the multi-objective is also used for the multi-objective case. So how these nearest neighbor are connected, that will be again based on the weighted sum of the distance in each plane when we are connecting these chunks while solving the multi-objective problem. And the third operator which we have changed is a guided mutation. So unlike the mutation which we see in genetic algorithm, which can give you a good solution as well as bad solution both. But in this case, you will see that this guided mutation is going to give you always the good solution. It's not going to give you bad solution. So how we are doing, this is the typical chromosome we have selected. First, identify the mutation site randomly. Once you have identified the mutation site randomly, re-index this entire chromosome again. So this mutation site is converted to 1. So remember, this entire tour is cyclic, so I can change the index. There is no problem in that. So if we change the index and make this particular index as 1, then we are breaking the connection site 1 and site 2. So site 1 and site 2, this connection we wanted to break, isn't it? So in order to break this particular connection, we need to find out the alternate connection. That's what happens in the 2-op. In the 2-op, there are 2 exchanges, isn't that why it is called as 2-op 2? So there are 2 exchanges are performed. So we are identifying the second mutation site Sj and site Sj to Sj plus 1, that we are identifying by comparing this particular distance. So first site is identified randomly, whereas second site is identified by looking at the distance. D1j in the kth plane is nothing but the distance between the CT1 and jth. So this particular distance we are comparing. So this distance is less than, let's say, D12. In that case, we are proceeding for the third step, and the third step again we are comparing the total distance. So D1j plus D2j plus 1 should be less than D12 and DJ plus 1. So what we are doing is this distance and this distance, summation of these two distance should be less than, this distance and this distance should be less than the earlier two distance. So if this is what happening, then the 2-op move is successful because the resultant tour will give you lower tour length with this, isn't it? So this is what we are performing randomly using a mutation procedure. So what we are doing is we are performing this NIT iteration times in the mutation operation. So clearly you can see that after the guided mutation operation, you get the good quality solution. You don't get the bad quality solution at all. Okay. So once we have developed this algorithm, then what we did is we have validated this algorithm first on a single objective optimization formulation. So here I am showing you the results for 1000 cities. For 1000 cities, you can see there is no cross connection at all. So it is very close to the global optimum solution. Again, we have solved 79 single objective traveling salesman problem. And what we have seen is the deviation with respect to the global optimum solution is just 1.8%. And we have solved the problems with cities varying between 14 to 16,860. In fact, if we solve a 10,000 city problem, we can solve in 1 hour on a desktop computer with a RAM of 16 GB. So even we have not parallelized it. If we parallelize it, we can solve even in a few minutes. Okay, so all right, please. Okay, so as I said that once we have validated this particular algorithm on a single objective problem, then we wanted to look at how it is performing on multi-objective. Because single objective anyway, local search algorithms are quite popular and they are working really fine. The idea was to develop it for the multi-objective. So in this particular slide, we have compared the results of hybrid local search evolutionary algorithm and the extended version, two-stage evolutionary algorithm. You can see that the hybrid local search algorithm only generates the part of the Pareto. It is generating only the part of the Pareto. Whereas two-stage evolutionary algorithm generates the entire Pareto front with the same number of function calculations. In the previous slide, as I said, that I am going to explain why it is happening. So see, typically in a genetic algorithm, the entire Pareto front is generated because of non-dominated sorting procedure. So see, the last point, whatever here are, these last points are assigned with the highest crowding distance. And that is how genetic algorithm favors the local exploration around that. But when you are solving the continuous search space problem, most of the explorations are successful. But when you are solving a combinatorial problem, most of these local explorations are not successful. And that is why the usual non-dominated sorting genetic algorithm, which can generate the entire Pareto front without any problem, is not able to generate the entire Pareto front here. Again, the another reason for that is, see, if this is the Pareto front, if I wanted to generate the point in this region, I am actually moving away from the utopia point. See, this is the utopia point, which is the theoretical based point, isn't it? We are minimizing the two distance in Pro B and Pro A simultaneously. So clearly, this particular point is theoretically based. So we are trying to move away from the theoretical base, and algorithm is not going to favor that. But let's say if we are generating the corner solution in two-stage evolutionary algorithm, what we are doing? We are generating this corner solution initially, and these corner solutions are seeded. When we are generating the corner solution, generating this in between point is easy. Why? Because now you are moving closer to this utopia point. In earlier case, you are going away from the utopia, and it is going to favor, isn't it? So that is the reason why two-stage evolutionary algorithm is able to generate the entire Pareto front without any problem, whereas this hybrid local search evolutionary algorithm only generated the part of the Pareto. Now this is the comparison with several state-of-the-art algorithms. You can see that we have compared our algorithm with several variants of non-dominated sorting, differential evolution, and conventional GA. And you can see that our Pareto front for same number of function calculation is much better, not only in terms of spread, but also in terms of convergence. Since we are trying to minimize the two distance in both these planes, clearly the solutions which are on the closer to this particular point are good. So you can see that our Pareto front in both these problems is much better. Again, we have extended this algorithm for different problems. So we have solved almost 55 multi-objective Euclidean TSP problems with varying objectives between 2 to 4. And we have compared our results with the multi-objective variants of lean Kernighan heuristic-based algorithms. And what we have seen is our algorithm is outperforming all these algorithms. In fact, just to check the scalability of our algorithm, we have again extended this application of this to a problem with 10,000 cities. And here the results for different cities I am showing. So these are the results with 100 cities, then 500, 1,000, then 5,000, and finally the 10,000 cities problems, the Pareto front are shown here. Normalized two distance in plane 1 and normalized two distance in plane 2 are plotted against each other. You can compare the lowest value here. This lowest value is very close to around 0.75. So if you solve a single objective problem, the typical value you get for a single objective gradient TSP is around 0.75. So which indicate that all these Pareto fronts are very close to the global axis. So in fact, that was the biggest size solved so far in the available literature. Then we have extended this idea of multi-objective traveling salesman problem to a dynamic problem. So dynamic problems are the problems in which even the locations are varying with time. They are not fixed, they are varying. So unlike the customers which are present at the one location, now the customer is also moving. Okay. So in this case, you can see that if you are solving the dynamic problem and the static problem, so here the light pink colored route is for the static problem. So this is the optimum route obtained for the static problem. And if you apply this optimum for a dynamic problem, we are going to get this particular route, and this is not optimum. This is not optimum. In fact, you get a different optimum route for a dynamic problem like this, 1, 4, 3, 5, 2, 1. So clearly, using the optimal solution solved for a static problem is not going to help you when you are solving a dynamic problem. That is what we are trying to illustrate here. Again, very often we don't want to use only one salesman. There could be multiple agents, isn't it? So in this case, we have used two agents. So how we can solve such problems? We can do the clustering of these cities. So in this case, cluster 1 and cluster 2 is generated, and cluster 1 is catered by the agent 1. Cluster 2 will be catered by agent 2, and each of these clusters will be solved as a separate PS, separate multi-object. Okay, so that's what is shown here. Okay. So as I said that this dynamic problem is nearly the same, except that now time also comes into the picture. So in this case, you can see that xi and yi, these are nothing but the coordinates in the kth plane for the ith city. But as you move from ith city to jth city, let's say, some time is going to elapse. And during that time, the position of this xi and yi are going to change, isn't it? So in this case, finding the time is very important, because these locations are moving in some velocity. So my new locations are going to be the previous location plus velocity into time. So this is how I can get the new coordinates. And these new coordinates I can use to find out the distance between the city I and j. And once we can find out this distance divided by the velocity of the salesman, that gives me the time. So this time is implicit here, and we have to find out this time in a trial and error. So this objective function is formulated here. So here we have to find out this time ti. So this is a quadratic equation, and we can find out the root of this quadratic equation using a Newton's method. And once we get the value of the time, then we can update the position. With this additional feature included in the previous formulation, we can solve even a dynamic problem. So just for a illustration, here we are showing the, we have purposefully generated the 4 clusters here, 4 clusters of the location. So this is plane 1. Similarly, we have used the mirror image of that as a plane 2. So if I'm using a mirror image of plane 1 as a plane 2, if I solve this as a multi-objective, I'm going to get unique solution, because both are same. Root is going to be same. But just for a illustration, I am not doing a complete mirror image of that, but only 2 locations I am keeping intact as it is. I'm not moving them as a mirror image. So if I do that, these are the Pareto front obtained for the static problem and dynamic problem. So this is the Pareto front obtained for the static problem, and this is the Pareto front obtained for a dynamic problem. So clearly both the Pareto fronts are different. They are not same. So again, then, okay, so 2 Pareto fronts we have obtained, one for a static problem and another for a dynamic problem. And we have compared the results in this case. So here you can see that if we look at the corner points of the Pareto front, if you compare, you can see that the corner point is basically what? Optimization of the objective 1. In that case, we don't get any cross connection here. So here the dotted line is for a static problem, whereas the solid line is for a dynamic problem. And you can see that the root for a static problem and dynamic problem are different here. So there is no cross connection here, but in plane 2 there will be some cross connection. Similarly, for a second corner point, there is no cross connection in plane 2, but in plane 1 there are cross connections. But if you take the in between point, there are cross connection in both the planes. All right. So in this case, again, we have solved the multi-cluster problem here. So we have multi-salesman problem we have solved. So we have taken a hub here, a depot here. From here, the delivery agents are going to go to each of these clusters, and we have solved these static as well as dynamic problem. So if you solve the static and dynamic problem, you can see that for the corner point 1, you can see that these are the results. So now instead of solving this entire cluster together, each of these clusters are solved individually. So you can see that the salesman is going from this hub, scattering here and coming back. So again, for a first corner point, there is no cross connection here, but in the plane 2 there are cross connections. In this case, there is no cross connection in plane 2. For plane 1, there is a cross connection when we are taking the second corner point. And if I'm taking the in-between point, we will have a cross connection in the both the planes. So this is just a comparison of HLSEA and TSEA on a dynamic problem. Again, you can see that TSEA is giving a better result in terms of hyper volume, and also the Pareto front, you can see it's a complete Pareto front result. We have again extended for a bigger size problems up to 10,000 cities problem, and you can see that the results are nearly optimal. We have again extended for the 3 objective problem, and these are the Pareto for the 3 objective problem. Okay, so this is the last problem. This is the marine access, this monitoring of the vessels in this marine. That is what has been done here. So in this case, total 172 ships are there in the marine, and we have tried to find out the optimization route for a static problem as well as dynamic problem. And you can see that for a static problem and dynamic problem, there is a different route. In fact, this work we are still continuing. Finally, the conclusion is we have developed a 2-stage evolutionary algorithm which can solve not only a single objective, multi-objective, dynamic, all type of variations, multi-salesman, etc. We have extended the idea of seeding in this case, and we have seen that the entire Pareto front can be generated with the seeding of the corner solution. And again, we have applied this for several problems like maritime surveillance problem, etc. Finally, I would like to acknowledge my students. So these are my PhD students. In fact, most of this work is done by Anubha. So I would be happy to answer any of your questions.